All right, how's everybody doing tonight? Okay. We've got the code up there for your attendance pin. If you don't have it in, I'll have it on the board as well. Assignment for this week is quiz 4, chapter 4 review questions, and that's it. And I believe I upped everything through the following Thursday in here, correct? Due date wise? Everything should be graded up to this point if you've turned it in up to week 3. If you're still late on whatever, make sure and get that in by Sunday. That'd be great, up to week 3. Tonight we're going to cover transmission basics on chapter 3, and then we're going to go right into the ping fax lab. In fact, I'm going to go ahead and pass out right now the ping fax lab because we're going to be using that right afterwards. Did you already print one of these out for you? Okay. Go. Thank you. Yep. This is not the most exciting chapter in the world, but it's a needed chapter because next week, you guys want to grab those handouts on the table. Next week, we're actually going to be doing cabling. And the first thing I want to do before we get started is kind of pass around the different types of cable the text talks about. It's one thing to read about it, it's another thing to touch and feel it and to do it and to live it. Okay, and so one of the things you'll be doing next week in networking, you will do quite a bit, some more than others, is creating crossover and straight cables. Right here, I'll pass this around this side. That's a straight cable. We'll talk more about that tonight. There's also a crossover cable, which is generally denoted by a red cable, which we have in the back. And then I've got a fiber optic connection as well. Fiber optic we'll talk about tonight, but it's a lot thinner, longer distances, and it can have components of either glass or plastic inside of the sheath. So you can pass that around. This next one, be kind of careful with. This is the original bus network we talked about when we went over the different topologies with the actual coaxial cable connected to a coaxial NIC card. So you maybe have never seen one of these, so I kind of pass these around too. You might actually walk into networks where you see those. Just be careful on the edges. You're not going to hurt anything. Those are unusable, so you're not going to hurt anything if you get oil on your fingers on it, no big deal. So I try to pass that out this session anyway, because this chapter is pretty dry and boring, okay? But what I like about it is next week, when you actually get to put some feet to what you read about, specifically the transmission media of Cat5, which is the most popular and the most predominant in networks, okay, that you'll be playing with anyway and messing with. Any questions on your guys' assignments for Thursday? I believe I changed all the due dates. If I didn't, forgive me, but I believe I did go through the entire semester and changed all the due dates in here from from Sunday to Thursday. So you have literally a week from tonight to finish week 4. And yes, quiet. Do you know what the password is? I have it on the board. Yep, I wrote it on the board too. Yep. If you didn't watch 23 News, I think I mentioned it to you about the iPad class starting next week, iPad development next spring. One of the reasons I wanted to do the news piece last night on the TV channel was there's a lot of questions from the community just on prerequisites, what do I need? And I highlighted it in the, there's a website you can go to, I'll put on the board, and you can go there, and it highlights the prereqs and things like that. It's iOS at rbc.us. And if you go there, it gives you prerequisites. But basically, since you're here, I'll go ahead and tell you what they are. Prereqs are C++ VB, either course credit or experience. Okay. Call letters for C++ would be CIS 276, or VB would be CIS 180, the entry-level courses. That'd be fine. Because the language you're going to be learning in the iOS development course is C Objective, or Objective-C they call it. And so if you have a C background, you're good to go. Even if you have a VB background, you're okay. The second thing besides programming background for prereq is hardware. I do require hardware, not recommend, but require. Even though we're going to be using Mac labs here, you're going to be needing to use a Mac all the time at home. So I put in the website, I believe, the latest Mac, either iMac, iBook, or any type of laptop, okay? MacBook, iBook, or Mac Mini. Mac Minis have if you're not familiar with them, are a lot smaller in footprint than a MacBook or an iMac, and they're about this big, about like that, about that thick, and they can hook up to your existing keyboard, mouse, and monitor, and they run about $500, brand new. You can find refurbished or used ones sometimes cheaper for sure. So those are the prereqs for coding, hardware, and that's it. So if you're interested in November 7th, the registration date for next semester, we're going to cap it out, I believe, at 24. I believe is what we're going to do, because that's all the Macs we have downstairs. And so it'll fill up pretty quick, I'm guessing. And so if you're interested, if you have more questions, you can give me a holler after class or email me. Be more than glad to answer any questions you might have. Okay? So let's go ahead and go on to this wonderful chapter 3, transmission media. I'm just going to highlight some of the components of chapter 3 that I think is important to note, specifically the types of media, okay, and where they fall as far as how they're used in networking. There's different types. You'll notice on the first bullet about the transmission concepts, probably the most complicated would be understanding full duplexing, which I don't expect you to understand reading one chapter. You're not going to. I've been in this for 25 years. I don't fully understand full duplexing, so don't expect you to understand it in a week. We'll touch it though and give you the overview, 30,000 foot view of this. Attenuation, latency, and noise we'll also discuss, which those are a little easier terms to understand. And then the different characteristics as you pass around the cables, specifically the Cat5 cable, the white cable, coaxial cable passed around, and fiber optic. The look and feel of these are totally different, and the uses for are as well. A little tip is, or clue, is the latency and noise. Those two attributes at the very top bullet have a lot to do with what I mean by that. What your work environment in will determine the media that runs your network. Okay, so if you're in a high noise area, more than likely it's going to be fiber, like a factory setting. If you're in an office area, Cat5 works fine. Okay, because that has fiber has a higher noise resistance than Cat5. Cat5 is a lot cheaper. You'll find that next week when you play with it. It's not made as well. It's not that it's not made as well. It's the components used to make it are cheaper than fiber, I guess is where it comes down to. And so for most offices, Cat5 works fine. Again, factory, industrial, you're going to see a lot of fiber because of the noise, maybe magnetic fields, things of that nature. And then latency, depending on what you need, like a factory could care less about latency. They just want to make sure the data gets there. They don't really care if it gets there in 5 minutes or an hour. They just want to make sure maybe data gets there possibly. So depending on your media, depends upon your type, depending on your area you work with, and the needs depends on the type that you're going to need to run that network on. And as you've already learned, we talked about this, a lot of networks have mixed media. Like here on campus, we have fiber from server to switches, from switches to your guys' computers all over campus is Cat5. Okay, just we're not a high noise area. The reason we have it from switch to server is for speed and for bandwidth purposes, more than likely for the noise and latency also, because we're actually running this alongside other wires underneath the floors. Because in our buildings, specifically this building and all the other buildings for the most part, the wires are underneath the versus a fake ceiling. Okay, and so a lot of buildings you work at will have a fake ceiling where they'll run it through. And we'll talk about some of the security reasons for that. This isn't network security, but in network security we talk about the network security ramifications, security ramifications of having wires run over a false ceiling versus maybe under a floor, which is a little bit more secure. The benefits of the different medias, principles behind different connector cables, and the wiring standards and best practices. So first is the word transmission. Regardless of what media you use, it's going to have a transmission basics that's going to be applied to all that media, whether it be fiber, whether it be coaxial, whether it be Cat5, whether it be wireless even. Transmission media is, and the basics are all the same. It's basically signals going across some medium of some type. Okay? In this case, it's zeros and ones. It's binary data going across the wires or the wireless and then being converted from binary to whatever format it needs to be on the other side. It might be media, it might be document, it might be text, whatever it might be, audio, okay? But computing hasn't changed really as far as what we're talking about tonight in networking in over 30 years as far as the technology goes. Now granted, we've gotten fast, it's gotten faster, but the basics that you'll learn in this class and also in your Cisco courses really don't change much. The basics do not change, okay? Now, other things might change, protocols, things of that you'll have to learn as you go along, update yourself, which I update myself at least 3 or 4 times a year, which it's not uncommon. So, and while we're talking about updates, I believe, did everybody get the link I sent you on the Network Plus certification website and all that good stuff? If you want more information on that, I know it's pretty self-explanatory on the website. You sign up, you register. I do have other resources I'm trying to get my hands on for you, like new resources. I'm hoping to have that in the next couple weeks, some maybe some CDs that will help you with test prep. That's what I'm looking for. I'm contacting some vendors to get some free stuff, which I want to get free stuff in your guys' hands. I don't want you to have to pay for that. For test prep, I don't believe for Network Plus or even Cisco or any of these courses, a lot of that stuff you can get free to prep for the test. Now, you will find websites and places that you can spend 10 grand on prepping, right? Believe me, you can. But I'm going to try my best to get you guys as many free resources as possible. Yeah, the back of your book will have a CD, or it should have, but some of you have a use text. You might not have that in the back of your book. And so if you have a new text, it will have some information in the back. But if you have a used one, don't feel bad. I'm going to give you guys, whether you have used or new, the newest and greatest test prep I can get my hands on, okay? So I'll get it. The vendors are a little slow the first part of the semester, but I'll get my hands on it. Transmission is the second part, which is basically the process of transmitting the data, and then the signal process after that transmission occurs, and then the receiving, transceiver, which is transmitting and receiving the signal. So see, these 3 components, these 3 legs of the chair make up a transmission basic. You've got the transmit, transmission, and transceiver on every type of media. Now again, it's going to get more complex and different protocols and things like that, but the basics are all going to be the same. Now when it comes to analog and digital, I know you've heard of digital, everybody in here, but some of you maybe not have heard of or played with or messed with analog at all. Anybody remember the old analog cell phones? Those are the cell phones that would, if you got, you could basically be connected pretty much and be almost, couldn't barely hear anybody like that, but it'd still be connected, all right? Digital, it's either on or off, and we'll talk about that, the difference between analog and digital. Basically, I always show this example in the class. It's like a light switch, digital is. You turn it off and on. There's no in between. That's digital. Analog is kind of like a wave. Okay, up and down, up and down, up and down. Not that it can't go off or can't, be canceled, but for the most part it's a wave. Whereas digital, it's either on or off. And we'll talk about that. But first, the first one it talks about here is voltage. Voltage is the current pressure going through that signal. Depending upon analog or digital, will be dependent upon the voltage. Depending on your media you use, will also be dependent upon the voltage. There is some voltage going through all media. Now granted, it's not enough to grab a hold of and shock you and knock you on the floor, but there is a little bit of voltage in there going across the lines. In fact, there are components you can buy that plugs into the wall. Say I could plug it in the wall in this room, go into another room, and actually have that component plugged into a server. And I could plug a Cat5 into the wall here that has a plug-in and get connection through electrical wires. You can actually run Ethernet over electrical, which has been out for a while actually. And I've used it in places where they couldn't run wires or some reason why we couldn't get it in, I can't remember. Generally it's because they can't run wires or they don't run on wires. This works fine. It's actually two plug-ins. One plug-in box plugs in where you're connecting your Cat5 from the source. The other plug-in box is where you want it to connect to, like in a basement or in an attic or in a house off-site. And as long as it's on the same electrical line current within that house or that structure, the Ethernet connection can run over electrical. And so most students don't know that either. And that's been out for a while. Some of you might have used it, and you can still buy the hardware for it. It's not as popular as it used to be when it first came out because of Wi-Fi. Everybody uses Wi-Fi now. There's probably most of you don't even use Ethernet anymore at home. I mean, you have Ethernet running from your modem to your Wi-Fi router. That's it. Everything else is Wi-Fi, I'm guessing. But every bit of media that runs across and has a signal has electrical current pressure. Then the other term is electrical signal strength, directly proportionate to voltage, and signal voltage. And then signals itself is a current, light pulse, or electromagnetic waves, depending upon the media, whether it be analog or digital. And we'll actually look at some graphs here in just a second. The first is analog. You'll notice how it's up and down. You've got your peaks at the top, and then you've got your bottom. And then you've got your in-between. That's your static kind of range that fits in between. So I mentioned cell phones earlier because you could literally be talking to somebody on a analog cell and signal, and basically it'd be garbled and you could barely hear them. That's because it's towards the lower spectrum of connection. It's still connected, but towards the lower spectrum. And then you could get, medium strength all the way to high good strength. And so this is just an example of an analog signal. You'll notice it starts on the left. There on the top left, depending upon the wave height, depends upon how much voltage is in that analog signal. And then you also not only have that, but you also have the time and length of that signal. And so voltage varies depending upon the peaks and valleys. Properties of an analog are amplitude, frequency, wavelength, and phase. In networking, for the most part, unless you go into a really old network, you probably won't mess with analog too much, if ever. Okay? You do need to know a little bit about it, just terminology-wise. But more than likely, you're not going to be working in this, especially in newer areas that you go into or newer businesses and new ventures. The amplitude in an analog is the wavelength itself, or the wave strength, whether it be how high it is, basically. So I always tell students, like a wave of an ocean, when it goes up high, the highest peak, that's going to be the wave strength. The frequency is the number of times the amplitude cycles over a fixed period. So say how many times it cycles every 5 seconds. Okay? And a cycle would be a full motion like this, one cycle, one cycle. It's measured in hertz, frequency is. And then wavelength is the distance between the corresponding wavelength cycle points. And basically on this one, all you need to know is it's expressed in meters or feet on the length of the wavelength. Here's an example of a wave with 90-degree phase difference. All this is two analog signals lapsed over each other with a 90-degree phase difference. One phase starts before the other. It's kind of like Michael, Row Your Boat Ashore and when you're singing it in stair step. One starts before the other one, is all it's doing here. And in analog, it did that a lot of times for redundancy. Okay, especially on cell towers when they were out, have a lot of redundant waves, just to make sure the data got where it's supposed to be going. The phase is basically the wave's process or progress over time in relation to a fixed point. That fixed point is whatever rules are set up when that analog signal is designed. Okay, that fixed point. So it varies depending on who sets up that network. Analog signals benefit over digital. It's more variable, meaning that the little subtleties of weakness doesn't drop it out totally. In digital, you'll find out there is no subtleties. It's either on or off. Analog, you could go very low and still have a weak, but still have a signal. Drawback of analog signal, it's varied and impressive voltage. It's susceptible to transmission flaws, drop data packets because of that. Digital signals, basically this refers to pulses of voltage, and the pulses refer to a binary 0 and 1. Okay? So you've got your 0 and 1 representation. Okay? Positive is 1, negative is 0, or 0 is off. 1 is on, 0 off. Okay? Just like a light switch. Okay? And so digital is where we're at today in networking, but that's not to say you might, I'm trying to think, only analog I'm thinking of would be if they have, there are old analog radio point-to-point satellites, that dishes type things that are still out. But that's about the only thing I can think of off the top of my head around here, around Rockford area, that's in use still. And it's literally a point-to-point dish pointing to each other using analog. Because all your cell's digital now, everything's digital. Networking, digital.
It's like microwave communication, right?
Yeah, it's like microwave communication, but it's point-to-point analog. And so, example here of digital, you've got at the top threshold 1, at the bottom 0. There is no waves. It's either on or off. Okay? And we know what that's like, right? Because if you have a cell phone, you either have signal or you don't. Now, granted, you have that little bar. That's really just to fake you out. You know that, right? That little bar just kind of, oh yeah, I got 2 bars. I got 1 bar. I got 4 bars. I got 2 bars. You know, it's software driven. The bars are software driven on your phones. On every digital device, they're software driven. Now, that's not to say, you know, you get closer to a tower, you get stronger signal sometimes. But what it has to actually do with is the electrical voltage that you have towards that tower. Okay. But it's either on or off. Whether you have 1 bar or 4 bars, doesn't matter. Does that make sense? It's software driven as far as the signals go. As far as that little, you know, the signal, the bars going up and down. So binary, since computers work in a binary world, you can guess that because of digital, definitely is a benefit to the computer age as far as new technology. Okay. Looks like I got a Facebook message, which I don't want that. See, I just lost my signal. I lost my digital signal. I need to sit down anyway. Come on. There we go, digital. Let's do it. Okay. Okay, now there is in this class, pct110, we do have one of the take-home labs where we do binary to decimal conversion and decimal to binary conversion. But again, this is just a basic overview here. Here is a composite of a snapshot of a binary component here. And it's a binary component of a byte, okay, which you might have heard of. You've heard of megabytes, gigabytes, kilobytes maybe. byte is the least common denominator when it comes to when you're talking about size within computer terms. So here's a byte. You'll notice on the very top row here, this row here, this very top row, it starts with a 0 and goes to 7. You have 8 bits, but since it starts with a 0 place, you have 8 areas, but it starts, most of you are used to the Dewey Decimal System, which starts with 1. In this, it starts with a 0 bit. So we have our 0 position all the way to 7th position, and then the next area, this line here, is basically taking that to whatever power. So you'll notice the left one there. Let me get rid of this here. You see that better? There we go. Starting from left going to the right, you'll notice the exponential power of this binary component starting 2 to the 7th power, 2 to the 6th power, all the way to 2 to the 0th power. Okay? All you need to remember is the bottom one when it comes to binary on positions. 128, 64, 32, 16, 8, 4, 2, and 1. You add all those up together, it should be 255, okay, going across, and that's the maximum for component of a byte, okay? And a byte is basically 8 bits together. When we get into the IP conversion, every IP address has 4 octets, and in between 4 octets has, you're used to maybe, you've seen, I don't know, at home you've used to maybe a 192.168.1.1. That's your wireless router IP address maybe for the server, right? You maybe have heard of that. Well, that 192, you can convert that to binary. It'll be 8 bits. It'll be a composite of 8 zeros and ones, dot, and then the other will be zeros and ones, 8, dot, zeros and ones, dot, zeros and ones. Okay? And so basically, you just note that every byte will have 8 bits. The computer's reading that language, so it understands it just fine. When you press a keyboard on your keys on your keyboard, it recognizes a ASCII equivalent of that, a number equivalent of that. But programmers have basically taken and made it easier for people to use. You don't have to think in binary, right? Users don't have to think in binary. They can just think in alphabet and Dewey Decimal. And so you find the decimal value of a bit. You basically multiply that, 1 or 0 by 2 to whatever the bit's position is, and then you have your value. And we go over that by hand. I show you how to do it by hand. Then I show you how to cheat, which is using a scientific calculator. How to do it that way, or on your phone with a scientific calculator. Which, by the way, they have some pretty cool scientific calculators now on the phones, on all phones. They're pretty sweet. Because some students are used to using maybe a certain type of calculator over the years. I know in manufacturing they do, and engineers I know. And what's cool about it now is they have actually the emulators that look just like the actual calculator they used in college 15 years ago. And it's on the iPad or on the iPhone or whatever. So it's pretty sweet. And because for years what they've been doing is just trying to figure out a way to do, they'd still do it with the calculator and by hand, but it's so much nicer to have that actual nice. It actually has, it looks like, the one I saw this guy showed me, it actually had scratches on it, kind of like you had, your old calculator you threw in the back of your car, little scratches on it and little dings in it and stuff to make it look real. So converting a byte to a decimal is just reverse. You determine the value of that bit, and then you add to it. All right? Converting a decimal to a byte, reverse the process. And if you're using a scientific calculator, you have a bin option, where you can type in a number, any number, doesn't matter what it is, and hit the bin button in the scientific calculator, and it'll give you the binary conversion, which I know everybody does that already, right? You will do that, by the way. You'll learn how to do that. It's very easy. Very easy to do. It's also really easy to do by hand, too, when I show you how to do it. It's literally one paragraph, step by step, of how to do it. And if you can remember that, or like I used to do, I keep it in my wallet to remember it until I finally had it down. And now literally I have not used it every day for like 5 years, so I still find myself having to get the piece of paper out. But I'll give you a little cheat sheet. You can use that, Because if you're like me, I kind of like to do it the old-fashioned way first, and then if you know how to do it the old-fashioned way, I don't know, it's not that our technology's made things easier, because it has, but I like to know how, kind of the nuts and bolts of how it used to be done and how I was taught to do it. I try to teach students that as well. So, but you'll go through that. All you need to know is tonight, analog waves, digital, zeros and ones, on and off. Done. That's all you need to know. Digital signal benefit over analog, it's more reliable, less noise interference. The digital signal drawback, now let's talk about noise for a second. Microwave noise, garage door opening noise. Noise could be from your TV. Noise could be from any device that generates power. Your washing machine, your dryer, your dishwasher. And you've all seen this at home. You've seen it happen. When you've turned on a device, you've had your TV close to that device or something, or your phone close to it, and something happened. You're like, well, what happened? My Wi-Fi's gone. I just walked by the dishwasher. What's going on with that? Okay. Again, interference. So the digital drawback or digital benefit is that it is less severe noise interference. It is not susceptible to noise like analog was. Okay. Analog was very susceptible to, say, microwaves in your house, and very susceptible to, say, garage door opener, just to name a few I can remember off the top of my head. The overhead on a digital is a non-data information required for proper signaling, which you didn't have in analog, and all that would be is the source. An example would be the source IP address where you're at to the destination IP address. Okay. In cell phones, they also have IP addresses and MAC addresses, just like your computers do. So it's the same concept there on cell devices. When it comes to networking, it's basically just the overhead has to do with the routing for the router to know, okay, where are you coming from, where you want to go, okay, and handing it off. Data modularization. This term basically is where the data relies upon some transmission, digital transmission. And a network connection may handle only analog signals. Here's some old school terms that I'll go over in a second here. Modem, when it comes to dial-up modems, it had what's called a modulator, demodulator. We still have them, by the way, in cable modems and DSL modems. But you could hear it in a dial-up because it would actually make a sound in this translation process. Data modularization is basically technology modifying the analog signals and making the data suitable over a communication path. Okay, so when, for instance, does any of you remember when you first maybe got DSL before cable came around? Remember that? Where it converted the analog line coming into your house through a modem, converting it to digital to your computer. Okay, the modem does the conversion part of that analog to digital, basically. Same thing with phones. A big thing, if you ever get a chance to, if I find a chance for you guys to do it this semester, I'll let you know about it. If you ever get a chance to go on a demo of voice over IP technology, I suggest doing that. In fact, there's a few places in town every once in a while that'll have like a dinner, it's called Learn and Eat or something, like they buy pizza or whatever, and then they have a vendor come in and show, like voice over IP demo or whatever. And there's a couple places in town that Entree was one that actually still does that every once in a while. So I'll find out if you guys can have that opportunity. I'll let you know about it. Even if it's on class night, we'll just say, hey, we're going to go there to do that. Because it is beneficial, I think, to see the new technology, especially voice over IP. And basically what that is, like here on campus, we have the largest voice over IP in the 4th state. When I say 4th state, I mean Missouri, Indiana, Illinois, and Wisconsin. We have the largest voice over IP setup. We've had people from China come and look at it. And basically what it is, the way we started with it anyway, was we had our analog patch wall of our phone lines coming in. 3Com came in and set up where it converted the analog to digital, and then it would go into the phone system in the classrooms and also in the offices, to where you could basically, when you picked up the phone, every phone had an IP address, and does have an IP address, just like a little computer. And if you hooked your computer to the phone, you could actually hook software to it to where when you called me, and if you were in my contacts or in this program, it would pop up your name, any information about past things we've talked about, right up on the screen. And so the benefit of that for sales and marketing and other types of businesses was, as you can imagine, just really revolutionized communication. And so that's voice over IP, which the reason I mentioned it was that last point there, making data suitable for carrying it over a communication path, whether it be DSL, whether it be voice over IP, converting analog to digital using data modularization. On this slide, all I want to make mention on data waves, or the wave term itself, is that depending on the carrier, they had unique waves, okay, of that device or of that medium, whatever it might be. That's all you need to know on that. Carriers had unique waves so they wouldn't collide amongst each other. As you can imagine, the different carriers, specifically cell phones, and even in networking, all these devices had different waves to run upon so they wouldn't collide. An example would be CBs that police use. There's different channels that they have. There's different reserve channels, meaning there's an emergency channel that only emergency folks can be on. Okay, there's if you're a ham radio operator, there's a ham radio operator channel range you can be on, and so you have to stay on that channel. If you stay on that channel, everybody's fine. Okay, same thing here. Depending upon the carrier, depending upon the wave and the transmission and the purpose. It also had in that where it would amplify that signal. Basically, it would be done by hardware, software combination, and you would have what's called repeaters that would modify and enhance. You can even buy repeaters for your house. In fact, I talked to somebody here a while back at their house where they have a repeater for the Wi-Fi. And so it just repeats that signal to go on further. On this slide, it just goes over the different types of carrier waves that could be in a carrier for analog. So we've got here at the top a carrier wave, an information wave in the middle, and an FM wave. Okay, FM radio is where that's referring to. And so you'll notice all of these are different in the wavelengths. And the reason they're different, one of the reasons they're different is so there won't be a collision or as much collision. There's always going to be some collision if you have them running side by side, but won't be as much collision because of the different wavelengths. That's all you need to know about that. This is the most difficult part probably, right here, the simplex, half-duplex, and duplex. Okay, then we're going to jump right into the media types that you guys I passed around. Then we'll take a break and then do the ping lap. So simplex is very initial technology when it comes to what we're talking about with analog specifically, and into the digital, but analogs initially because digital wasn't around. Simplex basically is one direction. Okay, let's see. What communication medium would you think of has a one-way communication? Two devices, but they can only communicate one at a time. I have one, you have one. Walkie-talkie. I push a button, I talk. Now, if you push a button and talk, well, that's going to happen. It's one at a time, going back and forth. Okay. Half-duplex is basically both directions at the same time. Okay. So in that realm, you go into the next ring after walkie-talkie, where basically you can have a channel open to talk all the time. But notice in this one, you have single and one communication channel. The single transmission is basically both directions, one at a time. One communication channel. This one is shared for multiple nodes to exchange information. Now on this one, where it says one communication channel, a lot of media outfits did use this for different types of media that they were sending out. So say they're a radio station, as an example, a good example. they would send out different different channels for different shows that were showing at the same time. Because they would have literally, if you've ever worked in a radio station, know somebody, you walk in, they have different booths and stuff. Literally might have 10 people, say, working in 10 separate booths, all communicating, right, at the same time, on the same, maybe the same channel, but minute, if you know about radio a little bit, they can be off by a .1 or a .2 in the radio dial. But it's, they own one license for a range of, like, say, 90.7 to 90.9 or something. So anyway, they would use this half-duplex to, specifically here, this one right here, we have one communication channel with multiple nodes to exchange information for that medium. Full duplex, this is single transmission, both directions simultaneously. This is where it began to be used on data networks, computer networks, okay? Both, all the time, constantly. As long as the machine's on, it's working, and it's doing its stuff. This diagram is a pretty good job as far as graphically showing kind of some of the differences. And you got to pay attention to the arrows on this one, really. On Simplex, you'll notice it's a one-way arrow, okay? It's only one way, that's it. Transmission, transmitter, and receiver, done, okay? The middle part, it does split it up. The bottom one is referring to the half-duplex, where you can actually break it up a little bit and share. But basically on this one, again, you have a transmitter and a receiver and data flowing through. Same thing here, transmitter, receiver, data flowing through. As you can see, the thing that's alike in all of these is all of them have a transmitter, all of them have a receiver, and you have data flowing. Now when you get to the last one on full duplex, you have basically this going on, the transmission, receiver, transmission, receiver. It just keeps going around and around all the time, okay? Continually flowing. Now I talked about CBs, police, emergency having different channels, because students have heard of that. Well, networking, you also have different channels built in, and we call them a little bit different in networking. You might have heard of the term subnet. Subnet actually came from this technology of channeling. Different channels on your CB dial, different channels on your ham radio. Anybody know anybody that did any ham radio type stuff or stuff? That's pretty cool, actually. That's a pretty cool thing. I never had. Do you want to know?
Until their antenna gets struck.
Oh, that's not good. I always thought that'd be cool to be a ham operator. I love that commercial where that guy goes, "Hey, can I quit my job and be a full-time blogger?" I think that's so great. We all wish we could do that, right? We can. But channel basically is communication of how things flow on a path or on a node. It's separated by physical or logical dimensions. And I think I mentioned already, the channel in networking refers to subnetting. In subnetting is a virtual thing, but it is logical, meaning everybody in here can be on a different subnet than, say, the next building or the next room. And when we do our stuff and talk to each other, it's not going to bother them at all. And when they talk and do their stuff, it's not going to bother us at all. Okay? And channeling helps in separating data. An example of separation would be voice and data. Those two. You're familiar with that with cell phone, right? You have your voice plan, your data plan, but you also have two distinct flows, one for voice, one for data. What do you think would happen if voice and data flowed on the same channel? Just think out loud. Just logically, what do you think could happen? Be collision, right? It would be very, very slow if it didn't collide to where you couldn't, barely a screeching halt. And so the separate channels help for bandwidth purposes, for collision purposes, for flow purposes, for rule purposes. I can have rules for data. I can have rules for voice. Now I will say by default, audio or voice is much beefier in data movement than data by itself. Data is data. Data could be text, generally it's going to be text of some type. let's talk about video for a second. Anybody, I know there's people in here who's played with video. Video editing, video editing on any type of network, or just let's talk about your computer for a second. Those of you who've done this before, when you edit a video, how intensive is that on your system? Just editing a video, processing a video.
Very
Pretty intensive on RAM. Takes a lot of your resources, right? And now let's say a Word document. How intensive on your processing is typing a letter or a research paper, which I know is coming up and you guys are dreading. Not very intensive, right? So your data is going to be separate and is separate on most networks for this purpose, for data flow, separating the channels either logically or physically, not causing collision, being able to have rules around it. And this last one on full duplex here, it takes advantage of that, using full duplex to increase the speed, okay, of that data flow. Okay, multiplexing. This is basically taking, all I need you to know on this slide is, multiplexing is where basically you have multiple signals coming in and it travels anywhere it needs to go at any time over that medium. That's all you need to know about multiplexing. Now multiplexing is on your NIC cards right now, the multiplexing technology. It's running all the time. It's looking all the time, listening all the time for information. And so all you need to know is multiple signals, whether it be data signals, audio signals, whatever, coming in. It's constantly, simultaneously traveling at all times using multiplexing. That's all you need to know about that for right now. This slide here just goes over on multiplexing. It highlights some of the benefits of multiplexing. In this one, it uses a time division. Basically, it splits it up into different times, and it can know what it is that's coming across it by the time that it comes across, basically, using multiplexing. So if I send a data packet out at 1201, then 1202, then 1203, then 1204, then 1205, but say I send out, we can understand that because that's stair-stepping it, but say I send out 10 packets at the same time at 1201, 1202, 1203, that's where multiplexing comes into play. Okay, send 10 items out at the same time. It sends it out, divides it where it needs to go, and ends up where it needs to go using multiplexing. Not going to go over that slide. Not going to go over that slide. Nope. There we go. Nodes. Let's talk about that one. Nodes is important when it comes to anything we're talking about, beginning networking, student. The first relationship in a node is point-to-point, and it's basically one transmitter, one receiver. Point-to-multipoint is basically one transmitter, multiple receivers. Broadcast, one transmitter, multiple undefined receivers. An example of point-to-point, the top one would be a point-to-point radio wave going to each other on a dish format. Point-to-multipoint, I'm on campus and I'm teaching and I'm casting it out to 5 different locations in this region when we have a satellite farm, we can do that, and point it to multiple receivers to receive it. Broadcast transmission would be an example of a TV station. Okay, broadcast their signal, and you have one transmitter, multiple undefined television receivers out there. It's used on wire and wireless networks for broadcast, and it's simple and quick for broadcast because it's an open communication. It's an open air communication for the most part. Non-broadcast is one transmitter and multiple defined receivers. So here's an example here of what I've already talked about visually here. Left one's point-to-point. We actually have some locations in downtown Rockford that still do this with their internet. They have Rockford Internet as an example. They still have some of this going on. What it is, these businesses will share, say they share a T3 line, okay, T2 line, T1 line, whatever. They share T3 line, T3 line, T2 line, T1 line, but they can also share communication between those lines. So say the building on the bottom actually has a T1 line coming into it. They can communicate to building 2 via the point-to-point transmission. And that building can then get internet and data transfer and all that good stuff from this type of technology. So it saves companies money doing it this way. The other is broadcast, I've already mentioned, like a television broadcast or radio broadcast, FM, AM, radio broadcast. Throughput and bandwidth. You guys have heard of this, hopefully before the class. Maybe heard that term thrown around. Basically on throughput, it just measures the amount of data that's transmitted during a given period of time, the capacity or bandwidth you have, and it's quantified by bits per second. The quantity of bits per second is your throughput. So again, the amount of data transmitted during a given period of time, what the capacity is, and the transmission of those bits per second. The bandwidth, and this is a strict definition, measures the difference between the highest and lowest frequencies that a medium can transmit. The range of frequencies on this one is megahertz, or hertz, I'm sorry. And bandwidth actually has to do with, easily define this one as, to where you can understand it, is an example of bandwidth is, say that we are needing more bandwidth in this room to download files from some server, okay? Bandwidth, by giving us more bandwidth, I can then allow our pipe to be bigger, basically, for stuff to download faster. Does that make sense? So the larger the bandwidth, the more stuff you can fit through the pipe faster generally. Not always, but generally. It's going to be faster if you have more bandwidth. And if you're familiar with, cable internet, you can buy different packages with Comcast and all these other providers of higher bandwidth, higher throughput. Usually it's synonymous in terms that they'll tell you, throughput, bandwidth, they'll say both. And basically all it's talking about is giving you a bigger pipe, basically, to download stuff through. And in turn, upload stuff through sometimes. So here we have terminologies as far as throughput and bandwidth, as far as how it's measured. You've heard of some of these already, but here's I'm going to focus on this part of it right here. A bit per second is BPS, kilobit per second, kbps, megabit per second, mbps, gigabit per second, gbps, and terabit per second, tbps, okay? These over here, the reason I focus on the right is most of you have probably heard of the mega, giga, and tera, I'm guessing. But if not, that's what it's there for. Bless you. Baseband and broadband. Baseband is basically digital signals sent through direct current or DC over wire, applied to wire. I believe I mentioned earlier about Ethernet. Ethernet is a baseband transmission. That's why Ethernet can run through the component I talked about earlier, which was 2 plugins plugged into your electrical wires at your house, electrical plugins at your house. It can run over DC current, electrical current, not DC current, electrical current. DC current, sorry. And when it runs over those wires, it actually can transmit data. But in and of itself, an Ethernet cord, when you plug it into your Cat5 cord into your NIC card, and then plug that into a router or a switch or another hub or another computer, there is some current going through that. And it's running over a DC current applied to that wire. Broadband transmission, you're familiar with this term. It's basically signals modulated, radio signals, RF signals, analog signals, and then it uses different frequency ranges. And it does not encode information as digital pulses on broadband. The reason broadband is faster than DSL, one of the reasons is it's pretty wide open in its coding. It doesn't have much coding to it, and so the transmission is going to be a little faster because of that. What slows down DSL is the decoding of it, encoding and decoding of that transmission. I'll end on this slide before we go to the actual hardware. Noise and types of noise are big in transmission flaws on media. Noise is any undesirable influence. It could be electrical influence. It could be a motor that's putting off electrical waves or electromagnetic waves. And the types of noise, EMI, which is electromagnetic interference, already mentioned, RFI, which is radio frequency interference. Now, radio frequency interference, a lot of your remotes use this still on radio frequency, RFI, to remote your TV, to remote your garage door, still around. Crosstalk, this is where wires cross amongst one another or near one another. That causes, like say if you do a Cat5 next to electrical wire, that could cause some crosstalk. Cat5 next to an analog phone wire could cause some crosstalk. Potential cause on this one, it talks about improper termination. What this is talking about is at the end of where that wire ends up, it's not terminated properly. When I passed around the coaxial with the coaxial Ethernet, those had what's called two caps on the end of that Ethernet wire or that coaxial wire that would stop it from flowing further. Well, in Cat5, your stop is actually built in to the wire itself. You guys will find this out next week. When you wire one end of your wire and test it with our testers, it can tell you how long that wire is. It will tell you how long that wire is and whether it passed its connection, because it has built-in termination in the wires itself. Environmental influences could cause noise, like heat. We could say cold could cause it too. Freezing temperatures sometimes could cause it. Frozen lines, things of that nature. So here we have a visual of a crosstalk between wires and a cable. And we'll learn this next week when we do our twisted pair lab. These wires and these Cat5 cables are twisted, and basically the more twist in the wires, the better. You want the most twisting as possible happening. The more twisting, the better, the less noise susceptible. You'll notice here where the gaps are is where the crosstalk happens. Okay, and I'll teach you that next week when we're doing our cabling. One of the things you want to just watch for when you do it is when you're holding your wire, you'll hold it pretty tight to where what's below here doesn't untwist, basically, while you're putting together your cable and making sure all your wires match up and everything. Okay, now let's see. I want to forward fast here to the actual medium. There we go. All right. Fiber optic. You guys saw that, right? The little fiber optic I got passed around. Here is a copper wire to fiber media converter. Basically on the right side is where you would plug in the RJ12 or RJ45 plug-in from, say, a Cat5 connection, and on the left it goes out to fiber. And this fiber actually has a two-prong fiber connection right here. Two-prong, two wires running into it. Coaxial, starting with the conductor core here, and then you've got your PVC Teflon coating around that, your shielding around that, and then your final sheath. So basically you've got three basic coatings around that initial core, and the central metal core, often copper sometimes, is surrounded by this insulator. It's braided metal shielding around that, and then finally the sheath over the top of the jacket that covers it. Very high noise resistance because of what we just mentioned. It's covered very much so and very tight. It's not loose at all. The advantage over twisted pair cabling, like we'll do next week and we'll talk about in a second, is it can carry signals farther before amplifying. And an amplifier is like a switch or a hub or a router. Generally terminology in networking for room-to-room amplifying is going to be hub or switch, okay? And basically what that means is, so say every 150 feet, you need another switch in there before you go on further in a Cat5 scenario. In a coaxial, you might be able to go 450, 500, 600 feet before having to have that duplicator amplifier. Disadvantage over twisted pair, it's more expensive. Hundreds of specifications within this realm. Different companies, when it was really at its heyday, made a lot of money in coaxial. It wasn't that it was not efficient, because it was. It wasn't it couldn't travel long distances. It could. It was expensive. And so that's actually how Cat5 came about, because of that. So here's some of the data coaxial cable progression, evolution. You've got basically the American wire gauge has these sizes for the usage of the data: RG6, RG8, RG58, and RG59. These again are just protocols, procedures, everything to do with the type of sheath, the type of covering, the type of wire, the type of mesh. All that is in this, the rules for the different networks it's being used on. It has what's called an F-type connector, and then the BNC connector is actually what you guys saw when we passed around the NIC card with the BNC connector. This one is probably what you're used to seeing on coaxial, and it's basically like you see at home with your cable. This is what we're going to be doing next week, was a twisted pair. It has 4 pairs, and there are from 0.4 to 0.8 millimeters in diameter. They're encased in a plastic sheath over copper wire, very fragile for the most part. And the important part of this is the twists stay intact below this area here. And I'll show you how to do that next week. Twisted pair, more twists per foot means more resistance to crosstalk, higher quality, and more expensive. Because the more twists you have per foot, the more wire it takes. Okay, so the tighter they twist it in manufacturing, the more wire they get. You know, so if they do loose twist compared to tight twist, it could be literally on loose twist, maybe we'll say this much wire. On tight twist, it might take this much wire, okay, because of the twisting in the wire. The twist ratio determines, again, the resistance, high quality, more expensive. High twist ratio, greater attenuation of data as it flows across it, because data is going to be less likely to drop. And when you have noise causes drop packets. Crosstalk causes drop packets, and so if you have more expensive Cat5 cabling, you're going to have better data flow. Hundreds of different designs. We buy ours from J-Tronics here in town. It's in the back of the room. You can see them there. It's called AMP on the side of the box, Tyco, AMP. And if you ever want to go buy, you'll learn next week the kit that we use. You can buy, as a student, you can go to J-Tronics and buy stuff, and they're pretty reasonable. They're cheaper than a lot of places online, and you know, a lot of shops you go to buy this stuff. And the guys there are real nice. The guys and gals that work there are really nice to help you. So J-Tronics is downtown. They do cater towards businesses, colleges, but you can go in there and buy, you know, say a kit to create Cat5 cabling, for instance. Comes with some wire and your crimpers and your strippers, and you know, at a bundle price basically. So dependencies on these different designs of twisted pair is basically, and these will be different per company, the twist ratio, the number of wire pairs, the copper grade, the shielding type, the shielding materials. There's 1 to 4,200 wire pairs possible within twisted pair technology. The standard we use is a TIA EIA 568 standard, and they have different types of wires. We use a Cat 5, Category 5, but there's Category 3 all the way to 7. 6 is actually coming up, and actually more popular in today's world with networking. And with new networks, more likely like a Cat 6. It's just a better grade wire, more noise resistance, more expensive. Cat 5, though, is the most used today in modern LAN environments. Advantages, really inexpensive, okay? Example, for a 3-foot length of fiber, we'll say it's $5. We'll just throw that number out there, rough, and it could be more or less a little bit. 3-foot length of Cat 5, 3 cents. Seriously, when you're talking about buying bulk, you can get it down to 3 cents per 3-foot. So relatively inexpensive, flexible, easy installation, and like you'll learn next week, you can buy a whole bunch of wire and then buy all the parts to make your own wire fairly cheap. Now you can also go to the store, computer stores or online, and buy wires completely made, straight cable, straight or crossover cable, either one, very expensive. But you'll learn next week how you can make it yourself. It does save you some money. Now if you're running a building or a new building of a whole bunch of cables, it is cheaper to do it yourself, okay? But manpower, time sometimes dictates that not to be the case, and sometimes you might have to go out and buy whatever you need. But you'll learn next week how you can do it. And there is jobs, by the way, in wiring, creating wires and running wires and patching wires together in what's called a patch panel. If you're interested in that after next week, let me know and I can tell you where you need to do and what class you need to take. And there's some good money in cabling, just running cable. That's all you do. The spans are significant difference between requiring a repeater on a advantage here, twisted pair. Accommodates several different topologies, handles current faster networking transmission speed, which most of your transmission speeds for new computers are gigabit transmission speed, which is very fast.
So you have faster transmission rates on the twisted pair than you do on the coax?
No.
Okay.
No. It's comparable, but coaxial, I would say, really is still a little bit better. But you have to, it's made better. It's more robust and just made better, basically. Better materials. But it's getting better. I'm not saying it's, Cat 5 is good. There's nothing wrong with it. 2 categories of Cat 5 twisted pair is STP, shielded twisted, and UTP, unshielded twisted pair. The unshielded twisted pair is just what it sounds like. There's twist in the wires, but it's unshielded, and it's very brittle a lot of times, easy to break on those types. Shielded, a little softer wire, a little easier to play with. So here we have a shielded twisted pair, individually insulated, as you can see here, individually insulated. They're surrounded by metallic substance, a foil of some type, and a barrier to external electromagnetic forces. They may be grounded. Untwisted pair, that's the kind we're going to use. Okay? One or more insulated pairs, but you notice there's no braided metal sheath around it between the wires and the sheath, the outer sheath. There's no additional sheathing. It's less expensive, less noise resistance. But most networks run upon what we're looking at here and what you'll learn how to wire. There's the categories again, category 3 to 7. The differences is definitely going to be in quality, okay? 5 up, you're going to have higher quality in 5E than in 5, higher quality in 6 than in 5E, so on and so forth. What I mean by quality is the sheath is a little thicker. The wires might be a little thicker around the plastic around the copper might be a little thicker, just to help with noise resistance. The twisting's a little bit better. And we're going to end on this slide because you'll be beginning on this slide next week. You have your different color codings on Cat5. And this is unshielded, twisted. The trick is this. Let me show you. So you've got brown, stripe brown, green, stripe green, orange, stripe orange, blue, stripe orange, or stripe blue. Now some of these stripes, you'll find this out next week, are not that prominent. Okay? Some of them might look just white, and you're like, I don't see the stripe. And it's basically just deducing the other ones around it to determine sometimes what the stripe is. It basically looks just like, sometimes it might actually be just something like, let me see if I can get like a color here, like a green or something. It might be something like this. We'll pretend this is a wire here. We'll do like a wire there. And we'll do a green. This is supposed to be a green-white, green stripe. Sometimes it'll be like just a very little, if I can find it here, because you will see these on your, like that, that's it. That's all you get. And so you do have to watch for that when you're doing your lab next week, but that's about it. It's, you know, not all of them are like that, but I have seen where, you know, you have to look hard to see the stripe sometimes, okay? But the way it's going to work next week is you'll have basically a wiring color scheme that you'll use, one for one side, one for the other, crimp them together, test them, and you're good to go. Okay, you guys want to take a break or go right into the ping lab? It's up to you. Let's take a break and come back at, by this clock, we'll come back at 10 till. How's that? 10 till? And I did give you guys handouts, so we'll start right off as soon as you get back.